Hello students, how are you? So in the previous class, we have calculated that, okay, we can calculate the enthalpy of a reaction, or I would not say reaction, of a combustion reaction with the help of calorimeter. Now we will move to reactions, right? We have just talked about combustion reactions. Now we will move to a general statement that suppose in a chemical reaction, the reactants are converted into product, right? So we can simply denote it with this notation, that is reactant is getting converted to product. Now the enthalpy change related to that reaction change, okay, that reaction is called as simply reaction enthalpy, and its symbol is delta RH, okay, that is enthalpy of a reaction. Now we'll talk more and more about this enthalpy of a reaction throughout the lecture, and that reaction can be different type, can be of different type. It can be phase transformation, it can be in combustion, it can be formation. So we'll talk about each of this. Clear? Now if I talk in general, then the formula is given by, suppose you have to calculate the enthalpy change during a reaction, then it is simply the sum of enthalpies of product, okay, minus the sum of enthalpies of reactant. That's all. Okay, so it is basically the formation enthalpy. So we'll talk about the formation enthalpy. For now, just consider that enthalpy of the product minus enthalpy of the reaction. We can just write it in the form of more mathematical expression. Okay, so what we have done is we have taken AI, which is the number of moles of that product that are involved during the reaction, and multiplied with the enthalpy of that product. And we have done it for the ith number of product. Similarly, we have done it for the ith number of reactant. Now, this summation will give you the reactant product enthalpy. This summation will give you the reactant enthalpy. So product minus reactant, and that is the reaction enthalpy, right? That is the reaction enthalpy, where A, I, and Bi, as I have told, it is the number of moles of the ith component in the balanced chemical reaction. Clear? Now, for example, we have this reaction, which is the combustion of methane. So methane is being combusted in the presence of 2 moles of oxygen, and we are getting 1 mole of carbon dioxide and 2 moles of water. So what we will take? We will take the summation of enthalpy of the product with the multiplied coefficient. So carbon dioxide has a coefficient of 1. So enthalpy of carbon dioxide multiplied by 1. Water has a enthalpy of, suppose, HMH2O liquid. So we have written it in this form. We have multiplied with it 2. That is the coefficient. So this is our overall product. Okay. Now what about the reactant? So we have 1 methane mole. Okay, 1 mole of methane. So for that we have written this. So this is basically molar. So we are writing M here. Okay. That is, it means that this enthalpy is given for 1 mole of methane. This enthalpy is for 1 mole of water. So we have multiplied for 2 mole of water. Similarly, this is the molar enthalpy for oxygen. So we have multiplied again with 2 to get for 2 moles of oxygen. Right? So it is mentioned here also that HM is the molar enthalpy. So what we have done is product minus reactant, and we got our enthalpy change. Okay, or the enthalpy of reaction. Now the enthalpy of reaction is very important quantity. It helps you to design a reaction in this way, right? So suppose you have conducting a reaction. If you know what are the required condition, whether the reaction is exothermic or the reaction is endothermic. If it is exothermic, it means that the heat is being liberated throughout the reaction. So if you want to say increase the rate of reaction, or you can say favor the product more and more, what you have to do? You have to keep the reaction in a colder condition, so that the Le-Chatelier principle will guide your reaction towards the product. Clear? Similarly, if you are dealing with an endothermic reaction, so what you will do? You will provide more and more heat accordingly, so that you can get a faster, or you can get a greater amount of product. Clear? So by knowing the enthalpy of a reaction, we can do such things of controlling the product concentration. Okay. Now it is also required to calculate the temperature dependence of equilibrium constant, because equilibrium constant is dependent upon the temperature, and in reality temperature is the only one which changes the value of equilibrium constant. You know it very well. Okay, because equilibrium constant is independent of number of moles you have taken in the reaction, mass of the substance, or anything. It is totally dependent upon the temperature. It is only and only the function of temperature. Clear? So enthalpy of a reaction depends upon the condition under which the reaction is carried out. First of all, it is therefore necessary that we must specify some standard condition. The standard enthalpy of reaction is the enthalpy change for a reaction when all the participating substances are in the standard states. So what is the meaning of this three statement? So see, whenever we conduct or we define something, we want it globally accepted, right? To make it globally accepted, what do? We take a common line that is common for all of the world, all of the researchers that are conducting this experiment or doing this experiment, right? So what do? We take a standard condition, and that standard condition is the necessity now. Okay. And whatever reactions we do, we take that standard condition only, and that enthalpy change during that standard condition is called as standard enthalpy of reaction. Clear? And also the participating substance should also be in their standard state. Now we'll talk about the standard state. What are the standard states and all? So first of all, suppose we are talking about the standard state of oxygen. So if you take oxygen in a standard condition, so standard condition is basically normal temperature, that is 25 degrees Celsius, and your atmospheric pressure, that is 1 atm. So if you take that specific condition, you will find that your oxygen is present at gaseous molecule, and the most stable, thermodynamically stable form of that oxygen is your O2, right? So therefore O2, if you are taking O2, then your compound that you have taken is in the standard state. Sorry, the element you have taken is in the standard state. Clear? For example, the standard state of liquid ethanol at 298 Kelvin is pure liquid ethanol at 1 bar. So that is a very clear definition. So similarly, if you talk about iron, so iron is in the solid form at 1 bar pressure and 298 Kelvin temperature. So usually the standard temperature is taken as 298 Kelvin or 25 degrees Celsius. So this is being denoted. So if you're talking about standard conditions, so what do? We know that this is the enthalpy change for symbolization. We just put a not sign here. So that will denote that your enthalpy change is for standard condition. Clear? Okay. Now, first of all, let us talk about the enthalpy change during phase transformation. So as I have told, the enthalpy change can be for any reaction. So the first reaction that we are interested in is in the phase transformation. So what is basically phase transformation? So phase means we are changing from one phase to another. Say we are going from gas to solid, solid to liquid, or liquid to gas. So that is called as phase change. Okay. So we will take a illustration of water. That is a very simple component to deal with. So what do we take? We take water in a liquid form, and during that process, we heat it, okay, and convert. So we have taken solid and we are converting into liquid. So what we are doing, we are raising temperature here. Clear? So we know that ice is present at 273 Kelvin. So it is in equilibrium with ice, and your liquid, means your ice and your liquid form of water, is present at equilibrium at 273 Kelvin, right? Now, the enthalpy change during this reaction is called as delta fusion enthalpy change, and that is taken as standard enthalpy change. Okay, so it is 6 kilojoule per mole. Okay, so to convert 1 mole of ice from solid state to the liquid state at 273 Kelvin requires 6 kilojoule mole of energy. So this is the meaning of it. So if water freezes, then the process is reversed. So if you are moving from liquid to solid, then what we have to do? You have to remove 6 kilojoule of energy from per mole of water, liquid water, at 273 Kelvin to convert it into what? To convert it into solid state, right? Clear? So in the forward process, it is called as delta H fusion naught, means fusion enthalpy at standard condition. And in the opposite case, what you are doing? You are condensing it, right? Okay. So melting of ice is endothermic. So we all know it. So if you want to melt ice, you have to provide energy. If you want to say fuse it, then the delta H fusion is positive, right? So if you want to fuse it, you have to take energy from it. Okay, so no, not fusion, about the say condensation. Okay, about the formation of ice, this is always negative. Similarly, we can consider another transformation of water. If you're going from liquid to gas, then in that case, again, you are going from liquid to gas. You have to convert your gaseous molecule. Okay, sorry, liquid molecule to gaseous molecule. So what you will do, you will again supply temperature. So that also will be requiring energy, and that process is called vaporization. So the heat involved at standard condition is delta H vaporization. So temperature we take it as 100 degrees Celsius, because this is the point at which the evaporation starts to take place, right? Clear? Okay. Now sublimation is direct conversion of solid. Now we are talking about what? Going from solid to gaseous. So for that we take CO2, which is also called as dry ice. So it starts to sublimate, or it sublimes at 195 Kelvin with delta H sublimation. Enthalpy change at standard condition is equals to 25.2 kilojoule per mole. Similarly, naphthalene sublimes slowly, and for this the summation enthalpy change during summation is as 73.0 kilojoule per mole. Okay, clear? Okay, so for this you have to take the temperature. If you're talking about phase transformation, and if you have to calculate the standard condition, then you will change the temperature. Your temperature will be no more 298 Kelvin. It will be that temperature at which the boiling start, or simply the boiling point of, say, water. If you're taking for the evaporation, if you're taking for the fusion, suppose you have to take the melting point. So that thing should be clear. So for that, temperature will change accordingly. Next is the same thing is written, that the standard enthalpy of summation is the enthalpy change when 1 mole of a solid substance changes to a liquid substance under standard condition and at a constant temperature. See, it is written very clearly. We are not saying it at constant standard temperature. We are saying it as constant temperature, and that temperature is the, so if you are talking about sublimation, so that is the sublimation temperature, of course. Okay, and the pressure is constant, but the pressure should not change. It should be 1 bar. What is the next? The magnitude of enthalpy change depend upon the strength of the intermolecular interaction. So that is a very common thing to understand, that okay, you have to break the bonds. If you have to move from liquid to gaseous, or you have to move from solid to gas, you have to break the bonds. So you have to sever the bonds, and for that energy is of course required. For example, the strong hydrogen bond between water molecules hold them tightly in liquid phase, so you have to convert it into gases, then you have to supply more energy. For cases of acetone, the dipole-dipole interaction is significantly weak, so for that reason you will require small amount of energy. So for acetone, okay, it will take more energy, where for 1 mole of water will take more amount of energy. So this is the table that we have. So if you have to move from solid to gaseous, okay, so this is basically what? This is enthalpy of fusion for all the solids. Okay, for all the solid enthalpy of fusion. Okay, so then we have the gaseous, right? So they have the enthalpy of fusion here. So this is a table, just you can look at it. So here's a question for you. The swimmer coming out of a pool is covered with a film of water, right? The weight about 18 grams, means the film of water which with the swimmer is covered, it is about 18 grams. How much heat must be supplied to evaporate this water at 298 Kelvin? Calculate the internal change of vaporization at 298 Kelvin. So two things you have to calculate: heat supplied and your internal energy. So these two things you have to calculate. Now the delta H vaporization of water is already given at 298 Kelvin. It is 44.01 kilojoule per mole. For for vaporization, you will need what? You will need 44 kilojoule per mole of energy to convert your water into gaseous form. So first you have to calculate the heat supplied at 298 Kelvin. So your heat supplied is equals to the del H vaporization. QP is equals to del H. Delta H, we know it very clearly. Okay. Now how we calculate the internal energy change? Say, so for 1 mole, first we'll calculate the number of moles. So it is 1 mole. For n mole, it is 1 into this. So that will give you the same value. So heat supplied is same. What about this? So we know this formula. Okay, for the simple formula is delta U is equals to delta H minus P delta V. We know that the volume change. Okay, we know the volume change. Okay, so we can put the values, all the values here. So delta Ng. So if in place of volume, we are taking what? We are taking delta NgRT. So since on the right hand side we have the gaseous molecule, therefore delta Ng is equals to 1. We already know delta H vaporization, R we know, T we know. Just put the values, you will get your answer, which is 41.53 kilojoule per mole. So we have talked about the enthalpy change during phase transformation. Now you will talk about the enthalpy change of formation. Again, we are taking the standard condition. So what is standard enthalpy change? So it is basically the enthalpy change when we form 1 mole of a substance from its element in the most stable state of aggregation, also known as the reference state. So you will get this thing more clear when you will see an example. So what are we saying here is that suppose we have to conduct CH4, right? We have to conduct CH4. So what are the elements that are involved? So we have carbon and we have hydrogen. So what do we take? We will take the most stable form of carbon at standard condition, more thermodynamically stable form of carbon at standard condition. Similarly, we will take the most stable form of hydrogen at standard condition. So that is called as the reference state or the standard state. and the enthalpy of means the enthalpy change that is undertaking the process during that, means if you just combine it all, then that is called as delta H formation. Okay, so that is the enthalpy change when that CH4 is formed from the standard state of carbon and the standard state of hydrogen. So the enthalpy change during this formation is called as standard enthalpy of formation. And when we are calculating it for the formation of 1 mole of that substance, we call it a standard molar enthalpy of formation. Clear? Okay, so for example, if I'm talking about the standard state, then for dioxygen is simply O2. If for carbon it is graphite, C graphite. For sulfur it is C rhombic. So this is the most important thing. So you should remember that, okay, carbon should be in the graphite form. You should take the graphite. If the standard enthalpy of, say, formation of, suppose, carbon diamond is given, then you cannot take it as the reference state. So that is completely wrong. Similarly, for the rhombic, it should be S rhombic, right? Okay, clear? And this is the overall thing. Now, if I ask, so in this process, you will form, suppose you are taking carbon, graphite, and oxygen O2. And the enthalpy change during the formation of CO2 will be the standard enthalpy of formation for the CO2. Now, if I ask what is the standard enthalpy of formation for graphite, then it is 0. Okay, so for standard state, the enthalpy of formation is always 0. Clear? So suppose I am taking it for water. So we found that the graphite has a delta H formation of, your H2O has a delta H formation of minus 285.8 kilojoule per mole. Similarly, for CH4, this delta H formation is for minus 74.81 kilojoule per mole. So what is the meaning of this? So when we are reacting this and we are getting liquid, so during this process, this much amount of heat is released. Similarly, if you are reacting C graphite with 2 moles of hydrogen, at standard state you are getting CH4. So this is actually CH4. So the enthalpy change during this reaction is the delta H formation for methane. Similarly, if we are forming C2H5OH, we have taken C graphite, H hydrogen, and O2 gaseous, and we are getting C2H5OH, and the enthalpy change during this reaction is minus 277.7 kilojoule per mole. Okay. Now you should remember this. So if you are asked that what is the standard enthalpy of formation for hydrogen or oxygen or graphite, hydrogen, oxygen, sir, all should be 0. Okay. So 1 or 2 things also you should remember, that what is the standard state of this special compound, like carbon, it is C graphite, sulfur, it is S rhombic. Similarly, for iodine, it should be liquid. Okay, it cannot be gaseous, it cannot be solid. For iodine, it should be liquid. Similarly, for mercury, it should be also liquid, because at standard state, mercury is a liquid. Now, let us talk about the standard enthalpy of formation more. So it is important to understand the molar enthalpy of formation. It is just a special case of delta RH. So it is just a special case of delta RH because we are actually calculating the delta H reaction only. But the special case is that the reactant molecule is in standard state, right? Okay. So here, if you talk about this, so is this the standard enthalpy of formation of calcium carbonate? No, because calcium should be there in the standard state, which is not present in the standard state. It is present as calcium oxide. Similarly, oxygen should be present as O2, which is not there. Carbon should be present as C graphite, which is not there. So the delta H, delta RH that is related to this reaction is not the delta H formation. Okay, so this should be made clear. So it would be, if this delta RH is been calculated from the standard state, then in that case we will say that, okay, your delta RH is delta HF. So that is the difference between your reaction enthalpy and your standard enthalpy of formation. Okay, clear? Now, also for this reaction, if you calculate it for delta H bromine, so in this case it is good. Why? Sorry, in this case it is wrong. So for this reaction, enthalpy is not the standard enthalpy of formation for HBr gaseous, right? This is not for HBr gaseous. Okay, so if you are calculating, you are doing it for 2 moles. Okay, so this reaction is not for standard enthalpy of formation, because we are saying that for standard enthalpy, it should form only 1 mole, but here 2 moles of HBr are formed, so this is wrong. Okay, so if you want to actually calculate it, so it will be 2 times the delta H. Similarly, we can do it in this way also. If you just divide this whole reaction by half, then in that case, whatever will the enthalpy change during the reaction, that will be your delta H formation. So you should be able to form only 1 mole, not 2 moles, or either it will be wrong. Clear? Okay. Now, if I give you this reaction, and if I ask you how you will calculate the delta RH of the reaction given the standard enthalpy of formation for each of these species. So what you will do, simply you will take the delta enthalpy of formation for the reactant, add this delta, so for the reactant add this, and delta enthalpy of formation for the product, and add this. Now do the subtraction from product to reactant and you will get your final delta RH. So that thing is already mentioned here. So what are we taking? We are taking the delta enthalpy of formation of the product minus the delta enthalpy of formation for the reactant at the standard state, and that will give you the standard enthalpy of reaction. Okay, is this clear? Now this A and B is what? Again, the coefficient of the product and the reactant in the balanced state. Now let us do and calculate it for a substance. So what we have done, we have taken COCO3 and CO2 as the product, and the reactant was what? CaCO3. So here is CaO, CO2 minus the product, that is CaCO3. So what do? We multiply it with the coefficient, the standard enthalpy of formation with the coefficient, and we got the final value of delta RH not as 178.3 kilojoule per mole. So since it is getting a positive charge, so it is an endothermic reaction, means the formation of CaCO3 is an endothermic reaction. Clear? So now let us move to this thermochemical equations more efficiently. So this is called as thermochemical equation, which is a balanced equation along with the enthalpy change. So this is overall called as a thermochemical equation. Now this equation is precisely describing the what? It is describing the combustion of ethanol at constant temperature and constant pressure, and the negative side is indicating that your heat is emerged during this process. Now it would be remembered to necessary the following things during the chemical equations. First of all, the equation should be balanced. Okay, the equation should be balanced, and the delta RH refers to the number of moles of substance by the equation, right? And it should have a unit of kilojoule per mole. So if you want to just illustrate with an example, here is an example of that. So what we have taken this reaction. So we know that these things we already know. Okay, for delta H liquid, the formation is what? Minus 285.83. Enthalpy change formation is this much. For ferric oxide, it is minus 82.42 kilojoule per mole. Now here is the quick kick for you, that we know that for iron, the solid state is the standard state, and I already told you that the formation enthalpy for the standard state is 0. So we have taken it as 0. Similarly for hydrogen, H2 gas is the standard state. For that reason, we have taken again it as 0. Clear? Now product minus reactant. What is the number of moles of water? It is 3. So we'll multiply it by 3. Similarly for Fe2O3, it is 1. So we'll multiply it by 1. Then product minus reactant, and that will give you the delta RH of the reaction. So that is giving you minus 33.3 kilojoule per mole. Okay, minus 33.3 kilojoule per mole. Note that the coefficient used in the calculation are pure number which are equal to the respective stoichiometric coefficient, so that you know already. And the unit of delta RH is kilojoule per mole, which means per mole of a reaction. Okay, now suppose we have one more reaction. Okay, so what we have done here is we have changed the coefficient. We have divided by 1. Okay, we have divided by 1. So in that case, what you will get? So divided by 2. Sorry, you have divided by 2. So what you will get? Whatever value you will get for delta RH, that will be 1 by half of the initial value. Okay, so it is mentioned here. It shows that the enthalpy is an extensive quantity. So this is the reason we have done it. So we have calculated it for the half of the reaction, means we are dividing by 1 by 2. Why we have done it? To ensure that the enthalpy change is extensive quality, because if we are just dividing it by 2, we are getting the enthalpy change as half. Next thing is, so these are the properties of the thermochemical equation. Okay, next thing is, if you have a reaction, okay, and if you are reversing the reaction, then the enthalpy change regarding that reaction, that will have a negative value of the initial value. So suppose this is the formation of ammonia, and the energy change, sorry, the enthalpy change is minus 91.8 kilojoule per mole. Suppose you are converting this reaction into degradation of the ammonia, then your sign will change. It will come with a negative sign. Next is Hess's law of combustion. So this all are the properties of what? This all are the properties of thermochemical equation. So what happens here? According to Hess's law, no matter what path you take, because enthalpy change is what? It is a state function, right? So if you are doing a reaction in two ways, suppose in the first path you are taking 2 steps and going to the product. In the second path you are taking 3 steps and going to the same product. Now if you add both of these equations, thermochemical equations, whatever the value of enthalpy change you get, that is same for both paths, because enthalpy change is path independent. Okay, so this is the Hess's law basically. Clear? So let us illustrate it with the help of example. Suppose this is the reaction that we are going. Okay, so this is delta RH. Now we are doing the same thing with a different process. Here also we got the same delta H. Okay, you can just go through it once again. So you will find that okay, this is having the same value, right? So we have illustrated this with an example. Clear? Okay, so this is the schematic representation of that. Suppose you are going from A to B directly, so that is delta RH. Suppose I am telling it as delta RH. Now suppose you are going to A, from A to C, then C to D, then B. Suppose A to C is delta H1, C to D is delta RH2, and D to B is delta RH3. So if you want to calculate delta RH, you will simply add these three, and whatever be the value is the value of the overall reaction. Now here's an example that is being taken. It is said that for the forward reaction, this value is minus 283.0 kilojoule per mole. Okay, what we have done, we have just reversed this reaction. Then what is happening here? The value has also been changed. Okay, the value has also been changed. Here what you have seen, so if you add two equations, suppose you add equation 1 and add equation 3. So what you will get? You will get an equation in which the stoichiometric coefficient are added according to algebra, and your delta RH is added. Okay, so we are taking summation of that, and we are getting it as minus 110.5 kilojoule per mole. Clear? So this is the overall Hess's law. So with this we have completed the Hess's law. This was for today's lecture. Thank you.